Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 3E. My name is Amog Dhamdere, and I will be moderating this session. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you all to the 11th International Congress on Information and Communication Technology, ICICT 2026. The 11th edition of this conference is being held in hybrid mode. The physical event was held yesterday in London, UK, and the virtual event is being held through Zoom from the 25th to the 27th of February 2026. I hope you will all enjoy the knowledgeable and interactive sessions throughout the day. In this session, we will have 6 presentations. Each presenter will be given 12 minutes for the presentations and 3 minutes for questions and answers. After the completion of 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any queries or updates, then you can write it to me in the chat box. Just before I start the session, I would now like to introduce you all to the session chairs for this session. Our first session chair is Dr. Napat Sukthong. I'm really sorry for the pronunciation, sir. Dr. Napat Sukthong is a lecturer in the Department of Computer Science at the Mahasarakham University, Thailand, with more than 20 years of academic and teaching experience. His areas of expertise include artificial intelligence, knowledge reasoning, spatial temporal reasoning, and machine learning. Dr. Sukthong is actively engaged in teaching and research, contributing to the advancement of intelligent systems and computational reasoning. Sir, I request you to unmute yourself and address the session by your opening remarks.
Okay. Good morning, good afternoon, good evening, everyone. On behalf of the organizing committee, it is my great pleasure to welcome you to Technical Session 3E of ICICT 2026. My name is Tapat Saktong from Mahasarakham University, Thailand. I'm honored to serve as the session chair for this session. We are delighted to have distinguished presenters and participants joining us from around the world. This session will showcase valuable research contributions in the field of information and communication technologies. And I am confident that today's presentation will stimulate insightful discussions and future collaborations. Thank you.
You're very welcome, sir. Our next session chair is Dr. Bhushan Chaudhary. Dr. Bhushan Chaudhary is an associate professor and head of the Department of Information Technology at SVKM's Institute of Technology, Dhule, Maharashtra. With over 18 years of academic experience, he specializes in artificial intelligence, swarm intelligence, and mobile computing. His research interests include database management, software testing, machine learning, and IoT-based solutions such as crop predictions, etc. Sir, I request you to unmute yourself and address the session with your opening remarks.
Yeah. So good afternoon, distinguished delegates, researchers, presenters, and honored guests. It's my pleasure on behalf of organizing committee of 11th International Congress on Information and Communication Technology to welcome all the presenters to this particular session 3E. I would like to express my sincere appreciation to all the presenters for their valuable contribution and participation in this conference. To all the reviewers for the rigorous evaluations, and to our attendees for being part of this scholarly exchange. With that, it is my honor to formally open the session. Let's begin with our first presentation. Thank you.
You're very welcome, sir. Our first presenter for today is Vindhya Senanayake, and the title of her paper is Data Constrained Deep Learning for Early Identification of Patients in Pandemic. Ma'am, I please request you to unmute yourself and share your screen.
Thank you so much. So I think, can you hear me? Am I audible to you?
Yes, ma'am, you're audible.
Thank you. Sir, can you see my screen?
Yes, ma'am, we can.
Thank you so much. Hi, everyone. So I'm Vindhya Senanayaka from Sri Lanka. So today I'll be presenting our work on data-constrained deep learning for early identification of patients in pandemic. So to begin with, let's move to the introduction. As we all know, COVID-19 was one of the major global health emergencies we have faced in recent years. So during the early stages of the pandemic, identification of people infected with this virus was very difficult, with some limitations of the standard COVID-19 identification method, the PCR method. As an alternative, chest X-ray images and the CT scan images can provide faster and non-invasive diagnosis for the COVID-19. So artificial intelligence can improve the COVID-19 identification process based on the medical data. But actually the thing is AI and deep learning models used for the image classification require a large number of data to perform well. So there is a challenge to achieve high accuracies with small image data sets. So this data scarcity problem is one of the major challenges in medical field because sometimes the data collection process is very expensive, time consuming. It depends on patients' privacy and ethical concerns. Not only that, sometimes the data collection process can practically be impossible, especially during early pandemic stages like in COVID-19. So one practical solution introduced for this data scarcity problem is transfer learning. So in transfer learning, you know that the main idea is reuse the knowledge from the source domain to a new task, even we have small number of images. Usually in many domains, large pre-trained models like VCG, Inception, so those are used. Those are previously trained on ImageNet dataset, which contains natural images. So these models are very deep and consisting with millions of parameters. So they require high computational power as well as the memory. So now moving on to the literature review section. I included several studies, related studies that use the transfer learning techniques for COVID-19 detection under the limited data conditions. So in the first study, they used a VGG16 model from 140 chest X-ray images. In the second study, they used 746 CT scan images with the DenseNet 169 model. Moving on to the next slide. Another study used 733 CT scan images with VGG19 model, and in the last study also they used VGG19 model on 738 CT scan images. Actually, since they use datasets less than 100 images, all of these studies apply the data augmentation techniques to artificially expand the datasets. Although data augmentation helps to increase the dataset size, it can introduce different kind of unrealistic patterns which are not suitable for the medical images. And this table in this slide summarizes the literature studies I have explained. So you can see in the last column of this table how large and complex these models. So they have more number of layers as well as more number of parameters. And also some of these presented models show some overfitting signs as well. So from the literature analysis, we have identified in medical domain, the common practice is to use the transfer learning with heavy models. So those models require high computational power. And also when training with small number of data, there is a risk to overfit the model. So in this study, our goal was to fill this gap by developing lightweight architectures that work efficiently in low resource environment for the COVID-19 identification using both chest X-ray images as well as CT scan images. So these are the steps of the methodology that we have followed during our investigation. And we use two publicly available data sets for chest X-ray images and the CT scan images, which collected from different hospitals. So we have considered three sub-data sets, which contain total number of images of 100, 500, and 1,000 separately for CT scan images and chest X-ray images. So from the table 2, you can see the description of the data sets. So we use these kind of subsets for the experiments to assess the learning behavior of the models when increasing the data sizes for the deployment in low resource environments. So in all data sets, we have two categories, COVID-19 positive and negative. So here we have applied basic image pre-processing techniques, and we didn't use data augmentation or some synthetic generation mechanisms to preserve the diagnostic integrity in medical data. And in this study, mainly we have developed 6 lightweight CNN models, 3 models for 3 chest X-ray datasets, and another 3 models for CT scan datasets. So we compared the model performances with transfer learning models, such as ResNet 50, Inception V3, as well as the VGG 19. So here we can see the structures of the proposed CNN lightweight models. So we designed simple architectures with 2 to 4 convolutional layers and with limited dense layers. So those architectures significantly have fewer number of parameters. So for an example, if we consider the model CNN model trained on 100 X-ray images, so it has only 55,413 parameters. When compared to the BGC 19 model, it has approximately 200 million parameters. So when it comes to the model training and evaluation, here we use separate external validation data sets with 100, 500, and 1,000 images from both X-rays as well as CT scan images. So we evaluated our models using validation accuracy, execution time, and the model complexity. So let's move to the experimental results. So here, the table in the left side of this slide, you can see that it includes the results of the translearning models on 3 chest X-ray image datasets for the COVID-19 identification. And right-hand side, you can see the results of the proposed CNN architectures. So for an example, when only using 100 images for the transfer learning models, it shows unstable validation performance. But when consider the ResNet 50 validation accuracy, you can see that it dropped to 50%. And in Inception V3 also, it dropped to below 40% for increasing the validation data. But on the other hand, you can see the proposed CNN model architecture's performances. So here, our lightweight model trained on 100 images achieved 91% to 94% validation accuracy with the lower training time, execution time. And also when the model trained on 1,000 images, both transfer learning models as well as proposed CNN models achieved same kind of validation accuracies, but the CNN model execution time is slower than the transfer learning models. So from this, that means actually even when increasing the training data, we can use computationally efficient CNN model architectures. And in this slide, you can see the results of the models, translearning models, as well as the proposed CNN models on CT scan datasets for the COVID-19 identification. So for the CT scans also, we have observed a similar trend. The translearning models showed high training accuracies, but weak validation performances on these kind of small datasets. And also, those models have overfitting signs as well. But when it comes to our lightweight CNN models, so those have competitive validation accuracies with less training time. So in overall, the performances of the CT scan is lower than the X-ray images. So in this slide, you can see the training and validation loss curves of the proposed CNN model trained on the 100 X-ray images and the ResNet 50 model trained on the same condition. So by looking at these curves, you can see that the proposed CNN model shows better stable convergence. And also when it comes to the ResNet 50 model, you can see that unstable performance with different fluctuations in the curve. So this shows the good generalization ability of our lightweight models under these limited data conditions. Not only that, actually, we have identified a relationship between the dataset size and the model complexity of the lightweight models. As dataset size increases, the model complexity also can
Excuse me, ma'am. I'm really
Um,
sorry to interrupt, but 10 minutes are up, so you can please conclude.
Okay, thank you so much.
Thank you.
When it comes to the conclusion, actually, our work demonstrates the lightweight CNN models outperform the large transfer learning models in limited data conditions. And also, we have noticed that X-ray images perform well than the CT scan images for the COVID-19 identification. And we have identified a clear relationship between the dataset size and the model complexity. Therefore, at the initial stage of a future emergency pandemic condition, we can use these kind of lightweight architectures for efficient disease diagnosis with limited data samples. So these are some several limitations of our study. So and also when consider the and finally these are the references that I have used to create the presentation. And yes, this is the end of my presentation, and thank you so much for your attention. And I'm happy to answer your questions. Thank you.
Thank you for your presentation, ma'am. I would now like to ask our session chairs if they have any questions for our presenter.
Yeah, am I audible?
Yes, sir.
Hello. Yeah.
Hello.
Ms. Vidya, in data constrained pandemic settings, usually data sets are often small, imbalanced, and noisy, right? So, could you elaborate on how your deep learning framework addresses issues such as class imbalance, overfitting, and domain shift? Because you mentioned somewhere that your model is somewhere mitigating the problem of overfitting as well, right? So, the domain shift to ensure the reliable early patient identification, no, that has to be somewhat elaborated, what I think. So you can just summarize that what techniques you have used for this purpose for imbalanced, noisy, and small kind of data sets.
So actually, from our experiments, we have used, for the experiments, actually, we have used balanced data set. In each category, the COVID-19 positive category and the COVID-19 negative category, we have used a balanced data set. But if there is a condition that we have unbalanced data sets, so then we can use some cross-validation techniques to overcome those conditions as well.
Yeah. My second question is, see, new pathogens were evolved over the period during pandemic, and clinical patterns were different for those pathogens. So, what are the remedies to overcome in your model to identify such new pathogens?
Yes, actually, this is a kind of primary study. We have developed this study only for the COVID-19 identification using chest X-ray images and the CT scan images. So when we consider different kind of future pandemic situations, you know that based on the disease, the variations of the images also can be different. But we can, based on our model, the relationship between the data size and the model complexity, we can get a basic idea about how we can design our model. So from that, we can initially take the start to develop our model, and when considering the pathological and the other variations of the data sets, in our experiments also, we have shown that for the CT scan images, for the feature extraction, actually, in the limited data conditions, it is very difficult because the results are lower than the chest X-ray images. So in chest X-ray images, we know that the images have a simple as well as more consistent structural variations in the X-ray images. So based on the image modality, we need to decide that.
Okay, fine.
Thank you so much for your presentation, ma'am.
Yeah, thank you so much.
Our next presenter for today is Sayaka Matsumoto from the Institute of Science, Tokyo, Japan, and the title of his paper is Extending TechQuiz for Life Cycle-Oriented Survey Quality Monitoring, Visualization of Response Behavior in Web-Based Surveys. Sir, I request you to kindly unmute yourself and share your screen.
Thank you. I have prepared a recorded presentation. May I play it now?
Please, and I'm really sorry to address you as sir. I'm really sorry.
Thank you. Good day. My name is Sayaka Matsumoto from Institute of Science, Tokyo. Today, I will present our study titled Extending TechQuiz for Life Cycle-Oriented Survey Quality Monitoring. In this presentation, I argue for a conceptual shift in how we understand survey quality monitoring. Rather than treating survey quality as something to be checked only after data collection, we propose to reconceptualize it as a life-oriented process. Traditionally, survey quality is evaluated after data collection. The focus is often placed on response-related and data completeness after the survey has been closed. As a result, visibility during survey execution is limited. This post-survey orientation has shaped much of survey methodology. However, the context of web-based surveys has changed the situation. In web-based surveys, missing responses are common. Respondents may interrupt the survey or abandon it before completion. Importantly, web-based systems generate paradata. Paradata reveal response behavior such as submission, timing, and response duration. In other words, we can now observe how respondents interact with survey over time. Despite this increased visibility, survey quality is still often evaluated only after data collection. This post-survey approach has important limitations. First, there is no systematic visibility during their execution. Second, operational issues such as stagnation in submissions may remain undetected. Third, structural issues in questionnaire design may emerge only after substantial dropout has already occurred. These limitations suggest the need for a different perspective. In this study, we argue for a reconceptualization of survey quality monitoring. we propose a shift from post-survey inspection to lifecycle-oriented monitoring. Survey quality should not be treated as a single-stage inspection. Instead, it should be understood as a process that unfolds across the entire survey lifecycle. This shift allows us to interpret response behavior as meaningful signals rather than simply as missing data. To operationalize this conceptual shift, we propose a lifecycle-oriented monitoring framework. The framework consists of 3 phases: the survey acceptance period, the survey completion phase, and the pre-analysis phase. Each phase is associated with a specific type of visualization. Although the framework can be applied as a practical workflow, it is conceptually structured to reinterpret survey quality as an ongoing process. The first phase focuses on temporal dynamics during the acceptance period. We visualize daily and cumulative submission counts. Instead of viewing submissions as mere numbers, we interpret them as participating unfolding over time. We may observe gradual accumulation, stagnation intervals, or deadline-driven spikes. From a lifecycle-oriented perspective, these temporal patterns are part of survey quality monitoring. The second phase focuses on response time during survey completion. In web-based surveys, response time can be recorded automatically. We do not interpret response time as a precise measure of cognitive load. Instead, we treated it as a proxy indicator of temporal response burden. Importantly, we do not rely only on the average completion time. We visualize the entire distribution. Response time distributions often show substantial variability, including long-tail patterns that may reflect interruptions or disengagement. Such variability is meaningful in lifecycle-oriented monitoring. The third phase focuses on response continuity and dropout progression. Through TechQuiz 1, we visualize individual response patterns. Through TechQuiz 2, we examine responses at the question level. Through the TechQuiz 3, we observe how response continuity progresses across the questionnaire. The motivation behind developing TechQuiz originated from observing large student surveys where many items are asked at once, especially at graduation. Although these surveys aim to collect comprehensive information, excessive length may lead to unintended dropout. Monitoring response continuity therefore becomes essential. Survey quality is not only about response rate, but also about sustaining participation until the final question. The strength of this framework lies in cross-phase interpretation. By connecting participation, engagement, and continuity, we gain a multi-layered understanding of survey quality. Importantly, missing responses are not treated merely as problems to be eliminated. Instead, they are interpreted as meaningful signals. Meaninglessness may reflect structural burden, temporal friction, or disengagement. In this sense, survey quality monitoring becomes an interpretive process rather than a corrective one. The goal is not to force completeness, but to understand response behavior across the life cycle. This framework is grounded in student survey context. It supports quality monitoring in surveys with many items and without mandatory response settings. By focusing on interpretation rather than enforcement, it encourages ethical questionnaire design. Although this study is situated in higher education, the conceptual approach may be transferable beyond education to other domains where missing responses are meaningful.
Excuse me, ma'am. I'm
In
really sorry to
conclusion,
interrupt, but you have
survey
2 minutes left.
quality monitoring should be life cycle oriented. By integrating temporal participation dynamics, response time distributions, and response continuity patterns, we move beyond post-survey inspection toward cross-phase interpretation.
Thank you for your presentation, ma'am. I ask our session chairs to address the technical session if they have any questions for her.
Okay, I got one question for the presenter. You use response time distributions and submission dynamics as indicators of survey quality. I would like to know that how do you distinguish between genuine respondent behavior, for example, fast but attentive respondents, and low quality response, such as random answering?
Thank you. Thank you for the question. I will ask my co-author, Professor Takamatsu, to respond.
Okay,
Okay.
I answer as I'm the collaborator. So you, as your question, it is difficult to distinguish the low quality and the random answering. But some case the whole answer is 11111 or the 2222. In this case, opposite. So the clearly the answer is not good. But so the some case the randomly. So I think that now it is very difficult. This is my great answer.
All right. Okay. Thank you.
Any more questions?
Okay, maybe one more. Do you see any potential for integrating machine learning or predictive analytics into the TechQuiz framework to automatically detect suspicions or low quality response patterns in real time? I mean, if you want to integrate with AI or analytics, something like that.
Great. So I will try. Thank you.
Okay, thank you very much. No more question from me.
Okay, thank you, sir. We can now move ahead with our next presentation by Kunihiko Takamatsu, from the Institute
Yeah.
of Science, Tokyo, Japan. And the title of his paper is Periodicity and Urgency Classification Assessment Matrix for Institutional Research Based on Edu-Informatics. So please unmute yourself and share your screen.
Okay. My presentation is I made a video file, and the time is 11 minutes.
Sure, sir, you can go ahead and present.
Good morning, or hello, or good evening. My name is Kunihiko Takamatsu. I belong to Institute of Science Tokyo. Today's my title of presentation is Periodicity and Urgency Classification Assessment Matrix, PLUCA-M for Institutional Research, IR, based on Edu-Informatics. Our collaborators are these members. This figure shows the recent key terms in higher education. I think most items already you know. Evidence-based education, EBE, institutional research, IR, learning analytics, LA, information and communication technology, ICT, digital transformation, DX. Slide show the Society 5.0. Society 5.0 is a concept for a future society. Japanese Cabinet Office defines Society 5.0 as follows. It refers to Society 1.0 is hunting and gathering era, and Society 2.0 is agricultural era, and Society 3.0 is industrial era, and now we live in a Society 4.0, information era. And the new society, Society 5.0, is future society. In Japan, Society 5.0 is very famous, but in the foreign countries, Society 5.0 is almost the same as Industry 5.0. In the era of Society 5.0, education is not the same as society from 1.0 to 4.0. For example, the OECD has proposed competency-based education, distinguish between technical and core competencies. OECD defines core competencies as delivery-related cluster, interpersonal cluster, and strategic cluster. Therefore, education in the 21st century includes both simple knowledge, the use of knowledge, and how to create new knowledge. We propose new field, Edu-Informatics. Edu-Informatics is a word combination between education and informatics. This figure shows the concept of Edu-Informatics. The field of education provides problem to be solved to Edu-Informatics. Oppositely, the field of informatics provide problem-solving method to Edu-Informatics. Challenge in institutional research is the inefficient mixture of external urgency and internal periodicity. IR practitioners are often busy with emergency tasks while managing routine, periodic work. This leads to ad hoc analysis that weakens long-term sustainability. Therefore, our research question is that how can we systematically classify IR activities to shift from reactive ad hoc analysis to strategic embedded intelligence? We propose the periodicity and urgency classification assessment matrix called PLUGA-M. This framework classifies IR activities along two axes. One is urgency, and the other is periodicity. Through qualitative analysis at Institute of Science Tokyo, our university, we identified four operational modes. One is deadline IR, one is emergency IR, and one is planning IR, and one is normal IR. This approach parallels ISO 14001 environmental management, which uses both normal and emergency response cycle. Framework identified four models. Normal IR covers routine, reporting, and standard request. Deadline IR represent cyclical high-pressure period, such as quality review preparation, happening again with predictable frequency. Emergency IR responds to unexpected situations, like the COVID-19 pandemic requiring rapid analysis without establishing protocol. And the key difference is that emergency IR involves questions the institution has never attempted to answer before. The fourth mode, planning IR, is proactive and internally motivated. It requires what we call time to think. Importantly, insight from emergency IR must be embodied into routine operations, not just documented. This means transforming crisis responses into permanent capabilities. As Professor Mori, he is my boss, emphasized, executive concentration in reactive mode eliminates the cognitive space necessary for strategic intelligence work. This slide shows our conclusion. Let me return to our research question. How can we systematically classify IR activities to shift from reactive to strategic intelligence? Our PLUGA-M framework provides three answers. First, organizations must protect capability for planning IR. Second, learning from places must be actively embedded into routine operations. Third, leadership must recognize that the time to think is not luxury, but necessity. This slide shows the future work. For future work, we plan 3 directions. First, we aim to test the PRUGA-M framework quantitatively across multiple institutions beyond Institute of Science Tokyo. Second, we will develop clear metrics to measure how IR units transition between operational modes. Third, we plan to integrate PRUGA-M with our existing informatics framework, including ABDAM-M and LSICL for a comprehensive approach.
Thank you very much. Do you have any questions?
Okay. Your framework is derived from qualitative analysis as a specific institutional context. I would like to know how transferable is PRUGA-M to other universities which have different governance structure, cultures, or resource levels, particularly outside Japan, for example.
Yeah, so the recently we collaborate with the Central Universities, IO, and other universities. So we will try this PRUGA-M matrix to other countries' university. So this is next our future work. Thank you very much.
Yes. Yeah. Thank you. No more questions.
Hello. Am I audible?
Hello.
Yeah.
Thank you.
Professor, how your proposed model be embedded into rapidly changing academic and policy environments here?
So now I have the good answer about the question. But so the recently in Japan, the government strongly require the rapid change against higher education. So we have to change rapidly. So in this case, I think it is very useful using this matrix. So in the future, so we will report the result. Thank you very much.
Yeah, my next question is, did you conduct any comparative study assess to evaluate the effectiveness against existing IR prioritization frameworks?
Yeah, so today, so I didn't show the detail about the compare with the other institutional framework. I think that it is a very famous is the OECD show some 3 layers. So in the paper that we deal with and explain or compare with this framework. So in the future, so please read our paper. Thank you very much.
Yeah, no more questions.
Thank you for your presentation, sir.
Thank you.
Our next presenter is Jérôme Roux from the University of Mons in Belgium, and the title of his paper is Revisiting Sabre in Qiskit toward a more consistent qubit mapping heuristic. Sir, I request you to unmute yourself and present.
Hello, can everyone hear me?
Yes, sir, you're audible.
Perfect, and you should see my slides right about now. Perfect. Hello everyone. Welcome to this presentation. As introduced, my name is Jérôme Roux, and I'll be presenting a work entitled revisiting Sabre and Qiskit toward a more consistent qubit mapping heuristic. The goal in this presentation, my goal will be to introduce you to qubit mapping in a very brief way so that you can understand what the Sabre heuristic is, what problem does it solve, and mostly what was our contribution to this heuristic in this work. Namely, in Qiskit, which is a library I will also introduce in this talk, we've identified an issue with the way Sabre was implemented. And in this presentation, I will introduce you to this issue, to the way we solved it, and try to quantify how impactful is this issue, because it's been running for quite some time, and there's many research that was produced using this issue. So it would be good news to see that this issue was not too impactful. And this will be what we will end up at the end of the presentation. So let us start with a very brief introduction to quantum computing and to qubit mapping specifically. So in quantum computing, a program is often represented as a circuit, which is what you can see here on the left. You have here 3 qubits, 0, Q0, Q1, and Q2, and a bunch of operations applied to them, and this circuit representation of a quantum program. But this thing here is really a logical object. Mathematically speaking, it can be modeled with linear algebra. So it's really a logical object, an abstract thing. And on the right here is a representation of a physical quantum computer. And what I represented here is 5 qubits, physical objects, physical qubits. And the connection between them represents the ability to apply these little vertical operations that connects several qubits. They are called CNOTs actually, but what you really need to know is that they are just involving these 2 qubits simultaneously, and they can only be applied on the physical qubits if they are adjacent, meaning that these 2 physical qubits, 0 and 1, can only apply these vertical operations because they are connected. 0 and 2 are not connected, so such a connection here between Q0 and Q2 cannot be done. And in red here is what the arrows represent what's called the mapping, which is the connection between the logical thing on the left and the physical thing on the right. Now, with such a mapping, it is still possible to execute this circuit if you transform it a little bit. And this little transformation is what's referred to as the routing. If I want to execute this circuit on this machine with this mapping here, I have to transform my circuit into this one, which is just changing this CNOT for this one and adding a swap gate here that will exchange Q1 and Q2 after this swap is executed. And this transformation is what's called the routing. And this routing depends on the mapping. If I had chosen another mapping that maps 0 in the middle here and Q1 and Q2 on either side, I wouldn't need to add any swap. And the goal of qubit mapping is to find the better mapping that leads to the better routed circuit. And better is here defined as the depth of the quantum circuits being as low as possible. The depth, I need to define it, and the depth is just the number of operations that you have in time. Here you have 1 gate followed by a second, followed by a third, so you have a depth of 3. In this case here, you have a depth of 1, 2, 3 for the 2 CNOT gates, and the swap counts for 3, so a total depth of 6, meaning that my first routing was actually worse than the second one. And this is the goal of qubit mapping, and this is the problem that Sabre solves. I know this introduction is very short, but I'm trying to remain within the time limits. So that's qubit mapping. Now let's delve to Sabre, its design, and its implementation within Qiskit, so that you can understand our contribution in this patch, Sabre, that I want to discuss. Qiskit is a library, Python library developed by IBM, used for quantum computing. It is one of the most widely used tool for quantum computing. And Sabre is an algorithm designed in 2019 that is the default qubit mapper in Qiskit. And to be precise, it is part of its transpile function. Sabre addresses both mapping and routing, And it does so in two of the 6 steps of the transpile function of Quiskit. And the layout part is actually the mapping part. They refer it to layout. But what's interesting for us is the routing part, because up to Quiskit 1.2.4, Sabre routing, which is the routing part of Sabre, contained this implementation issue I introduced earlier, and I mentioned earlier that I will introduce now. So let's take a look at Sabre. Here is a simplified explanation of what Sabre does. And if you take into account a mapping, a distance matrix that represents the physical graph that I showed earlier, a circuit, because you need a circuit, and what's called the front layer, which is just a set of gates, I will detail in the next slide, you will have at the end a circuit that is routed. And how you will get there is by doing these operations. And the algorithm, what it does is, as long as there are gates in the front layer, you are not done, and you need to repeat these operations. And what you do is, if some gates in the front layer can be executed, well, you don't get into this while at all. Instead, you just remove the gates and add their following gates to the front layer. But if no gates can be executed, so if there is a problem because you have a CNOT that you cannot do, well, you try to find some swaps that will make it possible. And the way to do so is by taking the swaps that will have the lowest cost with this little function h that I will also show in a few slides. So really, all it does is finding good swaps. Good as in they realize the minimum of some cost function. Now, for the details about the front layer, if this is your circuit and you label all the CNOT gates by a little name here from G1 to G8, you can establish this kind of graph, which represents which gate depends on which other gate. G1 and G2, they depend on no one because there is no gate before them. G3 and G4 both depend on G1 because they must be executed after G1. While G1 is not done, these two cannot be done as well. Meaning that the front layer at the beginning is G1 and G2, but once you've done G1, G3 and G4 will enter the front layer. Once G3 is done, G8 can enter the front layer because it no longer has unexecuted predecessors. And this heuristic cost for each swap that I mentioned earlier is given by this complicated formula. You don't need to understand all of it. Just know that it's basically a sum of distances between the qubits in the front layer here and the qubits in what's called the extended set, which is the thing that interests us the most in the following of this presentation. And the extended set is just the set of gate that is after the front layer. So basically, if G1 and G2 are in the front layer, G3 and 4 and maybe 5 and 6 will also be in the extended set. And so they will be considered to assess the cost of a swap. Now, in Quiskit's implementation, the extended set is a list of interactions between the physical qubits, meaning that if J belongs to EI, it indicates an interaction, CNOT, between the qubits J and I, and this comes with a reciprocity rule. If one belongs to the other, the first one must belong to the second, because if there is a CNOT between I and J, there is a CNOT between J and I. It's a both two-way relationship. And the problem is when you apply a swap, you need to update your extended set because it is stored in terms of physical qubits. The problem is this update is done through this method, which breaks the reciprocity rule in Quiskit. So let's see how does it break it and how to fix it, and then more importantly, the results, the experimental results. Excuse me. If you consider this as the extended set and you apply this swap, this extended set can be represented like this little graph. It indicates that qubit 0 makes a connection between 1 and 2, and it is reciprocated by these two entries here, leading to this graph. 0 is connected to 1 and to 2. When you apply a swap, you would like to just exchange these two qubits, meaning that you would like to get to this graph with 2 having a connection with 1 and 0. And this is what you should have in your extended set to store all these connections. But the current version does so in this way. The only difference is the entry number 1 here, so the one in the middle, has not been updated between this and that, where it should have been changed from 0 to 2. And it leads to such a graph where 0 and 2 have a normal connection, but you have these 2 arrowed connections, which represent one-way connections, which should not exist. So this is the current up to 1.2.4 update with the extended set, which leads to the issue I was mentioning.
Excuse me, sir. Really sorry to interrupt you, but
Yes.
you have 2 minutes left for your presentation time.
Okay, so I'll try to be quick. Thank you. Basically, what it does is that if you apply a swap, your gates will be counted with the wrong value. Instead of having this kind of contribution in the sum I mentioned earlier, you have this kind of contribution, which is not, in practice, not the same in many cases. To evaluate the impact of this bug that we've identified then corrected, we run on a number of circuits and a number of mapping selected randomly, rerouted them 30 times, and evaluated how whether or not the patch saber improved on the saber legacy, meaning that it led to better depth. And here in this table, basically the values, if they are lower than 15, they are bad values. If they are higher, they are good values. And we can see that the STD here is improved 30 times over 30 routings, 19 here, 30 here, 22 here. So it's always improved by patch saber, leading to the conclusion that patch saber is always more robust. But it's not always better, in the sense that the mean is not always consistently improved. This is also confirmed by this bigger table that I will quickly skip over to reach the conclusion. And briefly, the difference between the two algorithms is rather benign, because in most cases, they choose the same swap anyway, just they've given it different values, but it doesn't really matter. What matters is which one is the best. So that's why the bug is quite benign. And this is really the conclusion I want to make. You can read these if you want. It's that we've identified a bug that improves the robustness of the algorithm, but does not hinder its results too much. So previous established results are very trustworthy despite this bug being present for several years. And this work highlights the importance of algorithmic transparency and implementation correctness. Thank you for your attention. Sorry for the overtime. And if you have any questions, I'll be happy to answer them.
Hello, I have a question.
Yes.
Could you please elaborate on benchmarking methodology which you use to evaluate your enhanced qubit mapping heuristic?
Okay, so let me just go back to the slides. I went over this very quickly. So to test this hypothesis, we so to evaluate the two algorithms, we chose certain circuits. So the names are given here or in this here. The references to these circuits are given in the paper. I just didn't include them in the slides. They are classical circuits, and we evaluated. So for each circuit, we chose 30 mappings quite randomly, and they were fixed. But for each of these mappings, we routed them 30 times, and and this is one experiment. So we did 30 experiments for 30 mappings. And I think that answers your questions if I got it correctly.
Yeah, that was a very good presentation. No more questions.
Okay, well, thank you.
Okay, I got one question. How feasible is it to integrate patch saber into current Qiskit release, or are the quantum compilation to change?
Excuse me, I didn't quite get that.
How feasible it is to integrate your patch saber into current Qiskit release, or are the quantum compilation to change?
Oh, so it's in the latest version. It has been added. Because this, when we have identified this, we mentioned the team behind Saber through their GitHub, and since then it's been added already.
Okay, all right.
Nowadays, the latest iterations of Saber already include this patch.
Okay, no more question. Thank you very much.
Thank you so much for your presentation, sir.
You're welcome.
Our next presenter is Iputu Dodi Lesmana from the Sepuluh November Institute of Technology, Indonesia. And the title of his paper is Simple Deep Feature Fusion Learning with Efficient Hard Mining Triplet Loss for Improved Mosquito Classification. Sir, please unmute yourself and start presenting.
Okay, thank you. Okay. Good afternoon, everyone. In this presentation, I will be discussing our research on improving mosquito classification for vector surveillance, focusing on simple deep feature fusion learning and hard mining triplet loss with cross-batch memory. Mosquito classification is crucial for vector-borne disease control, where accurate species identification helps in tracking diseases like malaria, dengue, and Zika. And we rely on the CNNs to extract hierarchical morphological features, but interspecies similarity and intraspecies variation complicate feature extraction. Then a single polling operation, such as average or maximum polling, fail to effectively capture subtle feature differences. And hard negative mining in triplet loss methods is inefficient and computationally expensive, which leads to further difficulties in optimizing classification performance. To address these issues, we identify the weakness of single polling operation. As we know, as illustrated in figure 1, average polling weakens important features, especially in images with subtle morphological differences. And the maximum polling discards important smaller features. And gem polling is adaptive, but still suffer from single strategy limitation. To resolve this, we introduced a novel method that integrates multiple polling operations for richer feature representation. Our solution combines the simple deep feature fusion learning SDEPFL. This method integrated adaptive average polling, adaptive maximum polling, and gem polling to create compact and discriminative embedding, and the hard mining triplet loss with cross-batch memory, where this approach improves hard negative search efficiency by integrating with FAIS or Facebook AI similarity search, which enables low latency search and increases search efficiency by up to 4.7 times. In this slide, I explain the two main components of our framework. The first component is SDFFL. The SDFFL uses efficient NetV4 pre-trained on ImageNet with partial fine-tuning on the last layer. We modify the final MBCon block by changing the strike from 2 to 1 to preserve fine-grained spatial detail, which are important for distinguishing subtle differences between mosquito species. And then we apply 3 parallel polling methods: adaptive average polling, adaptive maximum polling, and gene polling. This capture global, salient, and detailed features. The poll features are concatenated into a single discriminative embedding. And at the XBMs applies triplet loss to pull same class sample closer and push different classes apart. To improve hard negative mining, we use cross-batch memory or XBM with store embeddings from previous batches to expand the search space. And then we integrate PIs for past nearest neighbors, making hard negative retrieval efficient. And finally, the optimized embedding form a compact and highly discriminative representation for accurate mosquito classification. We evaluate our method using 2 data sets. The first data set is primary data set consisting of more than 20,000 mosquito sample across 8 places with images taken from 4 angels and a resolution of 320 times 256 pixels. And the second data set is a Korean mosquito data set with more than 5,000 sample across 6 classes. And then we use AW optimizer, a learning rate of 1E4 and a batch size of 8 and 16 trained on a RTX 3050 Ti GPU. Our hyperparameter tuning show that the lambda equal 0.001 and alpha equal 0.1 were optimal for balancing metric loss and class separation. We evaluated the model on 2 datasets showing the improvements in accuracy and efficiency, where in table 1 present embedding performance on the primary mosquito dataset. All triplets with active ratio 100% were actively mined from memory, showing effective hard positive selection. And the negative distance from XBM is smaller than the batch negative, indicating better hard negative mining and class separation. The embedding drift is minimal, showing the stable feature, and the margin violation rate or P rate decreases from 93.30% to 35.71%, confirming good convergence. Table 2 compare our method with state-of-the-art model on the primary and Korean datasets. Our method achieves the best result with top 1 accuracy with more than 98% in the primary dataset and 99.78% in Korean dataset. F1 score more than in both dataset is more than 98%. The rank 1 is more than 98%, and the MEP is also more than 98%, outperforming the ResNet 50 and VGG 16. Using PIs also reduces search latency to 39.24 milliseconds in primary dataset and 41.09 milliseconds in Korean dataset, up to 4.7 times faster than non-PIs method. From our experiment, we found that as the EPFL improves the discriminative feature embeddings by integrating multiple polling methods, and then as the SBM maximize intra and interclass separation is a key for accurate mosquito classification, and the PIs enable efficient real-time searching, making the system practical for field development in mosquito vector surveillance. The method is also robust when using small batch size, making it efficient without compromising accuracy. In conclusion, we have successfully integrated SD-FPL and HD-XBM with FAIS for efficient mosquito classification. Our method achieves high accuracy in both dataset and deliver 4.7 times faster search time, making it suitable for real-time surveillance. And we demonstrate the robust performance with a small batch size, ensuring computational efficiency in real-world application. And this approach is not only useful for mosquito classification, but can also be adapted to other vector surveillance system. Thank you for your attention, and I'm happy to take any question.
Yeah. So have you checked for indirect parameters, like considering the fill conditions of varying lighting, occlusion, limited level data sets? So whether your mosquito classification model is robust with the real world surveillance environments? Have you checked for it?
Yes. The purpose.
So because
Sorry. Yes.
it was not mentioned in your presentation. That is why I am asking you.
Yeah. Yes. Sorry. I said it in. This is. Sorry. This is. Excuse me. Can you repeat again the question?
Do you want me to repeat the question?
Yes. Can you repeat again the question?
Yeah. So there are certain diversified field conditions, like varying lighting, occlusion. Then the data sets are very limitedly labeled. So this separation becomes very difficult in such cases, So have you taken care of this in your model?
Okay. Thank you for your question. Yes, the model addresses the challenges like varying lighting, occlusion, and limited dataset level indirectly through its design. The SDFFL combine multiple polling strategies to enhance feature extraction, making the model more robust to subtle variation in mosquito images, even under the challenging condition. Additionally, the hard mining triplet loss with crossbed memory have improved feature separation despite this difficulty by optimizing intra and interclass distance, which can assist in handling occlusion and lighting variation.
We find no more questions.
Thank you for your presentation, sir. Our next speaker for today is Jean-Philippe Valois from the University of Lille in France, and the title of his paper is Toward Scalable Exact Qubit Allocation Using Parallel Tree Research. Sir, I request you to unmute and start presenting.
Yes, thank you for the introduction. Can you hear me?
Yes, sir, you're audible.
Okay. Right, you can see my slides. Okay. Well, hello everyone. My name is Jean-Philippe Valois. I'm a first-year PhD student from France. And today I present to you the work I have conducted with Guillaume Elbec and Noureddine Melab, which is related to an application of high-performance computing for a problem related to the reliability of quantum algorithms, which is a work related to the presentation by Jérôme Rouzet earlier. First, I need to briefly give you a bit of context on quantum computing before formulating the problem. So I'll go pretty quickly over this because Jérôme has already presented these concepts, but the idea of quantum computing is that you have quantum circuits, such as this one, that encode a quantum algorithm. And these circuits, they involve qubits, which are the analog to regular bits in classical computing, referred to as logical qubits, on which certain gates or operations are applied sequentially from left to right. These gates can either involve a single qubit or multiple or 2 qubits at a time. And just like in classical computing, these circuits, they need to go through a compilation phase. And one crucial part in this compilation phase is to actually allocate these qubits on real physical qubits on a quantum device. So such a device can be represented as a graph, such as this one, where the nodes represent the physical qubits and the edges denote the possible 2-qubit interactions between them. So this defines the qubit allocation problem or the qubit mapping problem, which consists in finding a mapping between the theoretical logical qubits of the circuit and the actual physical qubits on the device on which it is executed. So you can interpret these physical qubits as available slots for the logical qubits to be placed in. So what's important to note is that these devices, they are in what we call the realm of NISQ hardware, for noisy intermediate scale quantum hardware, meaning that they are noisy, their operations performed on them present non-negligible error rates. So what you take out from this is that the shorter and the less gates your circuit contains, where the more reliable it will become when executed on a physical device. So with that in mind, let me quickly show you a simple example to showcase both the principle and the importance of a qubit allocation or qubit mapping problem. Let's say we want to allocate this circuit on this device. So we could start naively with this simple mapping encoded as this permutation. So in that case, the circuit remains the same. And you can see that the last 2-qubit gate is not directly executable because Q0 and Q2 are not next to each other. So we need to insert a swap gate that exchanges the states of 2 qubits, and then the last 2-qubit gate will be executable on the machine, but inserting these swaps come with a cost, as Jérôme Rouzet already showed you earlier, because they consist of 3 gates, and thus they increase the gate count and the depth of the circuit. So we could be a bit more clever and, for instance, start with this mapping, 102, and in that case, all of the gates would be executable without the need for an additional swap gate to be inserted. So with this simple example, you see that the initial mapping has a crucial impact on the resulting executable circuit, in that case with one which would be in theory twice as reliable as the other one. So concerning the related works on this problem, where most studies, they rely on heuristic-based approximate approaches because they are more common in practice and provide faster execution times, so they're allowed to solve for larger circuits. And on the other hand, exact approaches, which provide reference solutions, they are limited in scalability due to their computationally intensiveness, due to the high complexity of the problem for it to be solved exactly. So the goal of this work is to cope with this scalability limitation encountered by the exact approaches with the use of efficient parallel computing. So this is the formulation of the problem that we considered. So it's a standard quadratic assignment problem formulation from the literature, consisting in finding a permutation, encoding an allocation or mapping of size n for n-qubit circuit, such that it minimizes this objective function defined from two matrices f and d, which are derived from the quantum circuit and the quantum device, respectively. So how to interpret this formulation is that we find a mapping pi such that it minimizes the estimated number of swap gates that would be inserted for the circuit to be executable. So such a problem is NP hard to solve exactly with a such space of cardinality n factorial in that case, n being the size of the circuit. So how do we solve such a problem exactly? Well, we can now dive into the design of the parallel tree search algorithm. So in this context, we implement what we call a branch and bound algorithm, which consists in exploring all of the possible permutations by arranging them in the large search tree. So here's an example for allocating a 3-qubit circuit on a 4-qubit device. And the idea is to place 1 qubit at a time, building partial permutations that make up the nodes of the tree until we reach full permutations or mappings that can be evaluated using the objective function. And as we don't want to explore the entire tree, we employ a lower bounding operator, allowing us to discard unpromising nodes earlier in the search. So for that, we employ the well-established Gilmore-Lawler bound. And while this operator, it helps us to significantly reduce the search effort, while the size of branch and bound trees still grow exponentially with the size of the input, the size of the circuit, thus motivating the use of parallel execution. So concerning the parallel design, well, you may ask, how do we implement a parallel branch and bound? Well, for that, we can employ the parallel tree exploration model, which is a real challenge to implement because branch and bound trees are very irregular and unpredictable. So precisely, our implementation is based on a multi-pool design with multiple CPU cores that operate concurrently, and each CPU core or CPU thread, it manages its own pool of nodes, and these pools, they are used to process the different tree nodes represented as the black squares throughout the exploration until the whole search terminates. So, however, as such an exploration is highly irregular, as I just said, while some pools they might become empty much quicker than others. Therefore, we need to implement a dynamic load balancing mechanism. And for that, we use a work stealing mechanism between the processes. And to manage this work stealing mechanism, each individual pool is implemented as a double-ended queue with a private part used for its processor to perform the computations on the nodes, and a shared part used for the other CPU threads to still work at the same time. So this design, it allows to perform the computations and the communications concurrently, thereby maximizing the overall parallel efficiency and scalability of our approach. So now we can focus on the experimental results. So for the setup, our code is implemented in Chapel, which is a portable and scalable language providing a high-level abstraction for parallelism. And all of our experiments, they are conducted on the French Grid 5000 computational platform. So for the benchmarks, we considered quantum circuits of up to 20 qubits and targeting this device featuring 20 physical qubits. So we can begin by evaluating the scalability of our approach, consisting in measuring the speedup when increasing the number of CPUs. And this graph clearly highlights how our approach effectively exploits the resources, because on the 3 considered benchmarks, we are close to the optimal, the theoretical best speedup, ideal speedup, reaching up to 94% on the largest instance. And finally, we compare ourselves to the state of the art for this formulation, which is also a parallel branch and bound approach, but with the main difference being the lower bounding operator, which is much different. And here we see that on a variety of benchmark circuits, we managed to reach much lower execution times consistently, and thus yield substantial performance gains overall on most benchmarks. So now let me finish with some concluding remarks. So in this study, we implemented a tree search algorithm that allows to provide some reference exact solutions for the qubit allocation or the qubit mapping problem, where we address the scalability barrier through the use of efficient parallelism. And ultimately, this allowed us to provide state-of-the-art performance results on most considered benchmarks. So overall, this work, it places itself right at the intersection between quantum computing, optimization, and high-performance computing. So now, finally, a few promising directions for future work emerge. First one being to extend this work to internode parallelism, that is to exploit multiple compute nodes, thus multiple multi-core CPUs at the same time, and also to extend it eventually to GPU accelerated branch and bound to further increase the scalability capabilities. And also looking ahead, we could incorporate multi-objective optimization approaches, as well as exploring more sophisticated formulation than the quadratic assignment problem formulation employed in this study. And that basically concludes my presentation. So thank you very much for your attention.
All right, I got one question. Your
Sure.
parallel branch and bound approach shows strong scaling on HPC clusters. What
Right.
are the current practical limits in terms of circuit size or qubit count, where exact qubit allocation remains feasible using your method?
Yeah, that's a really good question. So recently, the highest provided exact solution only featured up to 16 qubits.
Mhm.
And here in this work, we extended it to 20, but we can actually reach, because here, all of the execution times you see, there are only a few seconds. So we could go further, and we know that we can solve up to size of 26. So that's the state of the art right now for the exact approaches, which are pretty scarce for this problem.
All right. Okay. Thank you. No more question.
Thank you.
Thank you for your
No
presentation,
questions
sir.
from my.
All right. Thank you.
Okay, thank you for your presentation.
Thank you very much, sir.
I now request our session chairs to give their closing remarks. Dr. Napat Supthong first, please.
Okay, this concludes our session. I would like to thank all presenters for their excellent contributions and all participants for their active participation. Thank you once again for attending this session of ICICT 2026, and I wish you an enjoyable and productive conference. Have a great day.
Thank you.
I would like to extend my sincere appreciation to all the presenters for an engaging and intellectually stimulating session. I would also like to thank Napat Suptong for co-chairing this session and being so thoughtful and putting some thoughtful questions before presenters. Thank you all.
Thank you very much, Dr. Pushan.
I sincerely thank our authors for their excellent presentations and contribution in this session, and all our participants for being a part of the international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 11th version and all the previous versions of this conference. We will be happy to have you in the 12th version in 2027 as well. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICICT 2026. I also thank our session chairs, Dr. Napat Sukthong and Dr. Bhushan Chaudhary, for chairing this session. A token of our appreciation to the chair on behalf of Team ICICT 2026 and Global Knowledge Research Foundation and partners. Thank you to all of you for your valuable presence. I kindly request all of you to switch on your camera for a quick snapshot of this virtual conference. Chirag sir, can you please take the snapshot? Okay, I think we're done. So yeah, thank you everyone. Stay safe and take care.
Thank you very much.
Thank you.
Thank you.